Hello, I'm Chris Athanas. This thing's in the way here. I'm a KMP developer, and today we're going to be talking a little bit more about the How to Program from the Ground Up series. We're going to be talking about parallel processing. Oh yeah, update from for the closing of the portal. The tech support guy came out here, and I actually was in the bathroom. I know. I hope that's not too YouTube unfriendly. So he left a note and he says he's gonna come back on Tuesday. So hopefully we'll get this. It was my fault this time. My fault. Okay, we'll get this thing closed up soon enough. All right. So parallel processing, concurrent program, also called concurrent programming. And the big idea is it'd be useful to do more than one thing at the same time on the same computer, or slicing up the computer into little time segments. So little bits here, little bits there, little bits there, little bits there. That's one way to do it. And as far as threads are concerned, it's kind of abstracted whether it's going to be on multiple CPUs, and it splits the task up between those ones. It's like you're eating a meal, and instead of eating the first course all the way through, and then you're eating the dessert all the way through, then and then you're the third course all the way through. You're eating a little piece of each course. You go get the buffet, and you load up the first course, second course, third course. And you just take a bite of this one, a bite of this one, a bite of this one. Buy this one, buy this one, buy this one. That's and the jobs are the bites. The jobs that are coming in are the things you're eating a little piece of. So that's the big idea. And then once you can divide your, let the operating system, whatever your program, to divide the task up into multiple tasks. Once you've thought your problem through that way, then it allows the computer to go, oh, I can just, you can have 1,000 CPUs now, and it'll just. Hopefully, if you structure it properly, make it go faster. Sometimes that's not the case. So I like to see the code for this first. Like, what are you talking about? It's like we're starting these things called threads, which is just like a instead of calling one function at a time, you're calling two functions at the same time. That's all that's doing. So this is how you define a thread in Kotlin. It's super easy. You say, I want a thread, and here's the function right there. Boom. And it doesn't start running until, and here's another thread, doesn't start running until you hit start. So then it calls this function, just brrr, so it goes there as fast as it can, right? And does a thread sleep. This just makes it pause for 10 milliseconds, and then it does it again. So this one and this one are both accessing the same shared resource. It's a shared resource. They're accessing the same variable, okay, in this case. It could be the same database, it could be the same network. It's the same thing that only has like one thing at a time can really go through it. Okay, that's what that is. Okay, so you start it, and then this join thing means run until you're done, and then wait, and then and wait here until you're done. So those will actually go. Those will actually go at the same time. This will go. That'll just wait, and they'll both be waiting at the same time. And if one goes first, it'll go. So both have to go through first, and then that'll print the value for you. So. And then the problem here was it's got something called race conditions. So here's the picture, right? Here's the picture here. So you have two things accessing the same variable. I'm being very pedantic on purpose because I was like, what are you guys talking about? Because they talk about this is going to solve all the problems, and they make it. Of course, they don't fully understand all the implications, what's involved. So they just heard that, just use threads. It's a real hard problem. Well, here's the bigger thing. This is called a sequence diagram. I am surprised how many people in computer science don't know that this is a really great tool to explain this problem. So here's the thread one, here's thread two, here's the execution from time. Guys, it goes to time. It goes through time from low time to high time. So it goes, marches through time as time marches on. So here's step one, read X. So thread one reads the shared variable X. It goes, oh, okay, it keeps a little local copy. And then it calculates it. Okay, and then this one does it. Thread 2 does it over here. And this should be a little diagonal. It shouldn't be straight, but just for purposes of keeping everything straight. Instead of going like this, it goes straight across just for making it more compact. That's all. So these are all in time, right? So it calculates the new value and then sets it, okay? Oh, this also, thread 2 also calculates that value based on the local value it has. Also sets it. So both sets it to 1. That's not what we wanted. We want that to increment the actual value. So now we have the value of 1 where it shouldn't be 1, right? It should be 2. But because of this race condition, whoever got there first is going to put the correct value, and whoever got there second is not. So they're racing this thing right here. They're racing here. This from between step 3 and 4 here. They are racing each other. It's indeterminate. It might go this first one, this one, and that's the problem, because these things aren't happening. We're not reading and writing at the same time. We're reading and then sometime later writing, and that's the thing you have to deal with. Now sometimes it gets it right. Sometimes it goes boop boop, gets it in there, and so everything's in sequence. But sometimes it's not. So that's the race condition. And you can see it here at the end result here, because we're just adding this value, 2 threads, adding it 100 times. Each one does it 100 times. It should be 200 at the end. Well, it's 190 because of this race condition happening. And let's talk about what can happen in a database. In a database situation when people aren't aware that this behavior exists, and you'd be surprised because they don't really teach this very well in college, or it's later on. It's like, oh yeah, it's a high-end course. It's like, this is come on. Okay, here we go.
One of the most successful, widely applicable architectures was a layered system backed up by a relational database. Something like this.
So basically he's saying, so he's got the layered system application, and it's hooked up to some database store, which is that like the shared resource variable. Okay, in his example, he uses a database. It's the same thing as having a variable, same thing.
It's a UI, some logic, and a database. For systems with a moderate number of users and relatively simple CRUD-style features, this was a very good choice.
CRUD means create, read, update, delete. So you're setting a value, you're reading the value, you're changing the value, and you're removing it somehow. We're not using that anymore. That's create, read, update, CRUD. It's CRUD.
Choice. I think that one of the reasons it was a good choice, though, is quite informative. I think a principal reason that the clever but slow idea of transactions in relational databases.
The transactions is where he's talking about this atomic things where you're getting the value, doing the mucking with it, and then setting it again, all in one transaction. Nobody can come in and interrupt it or read it. Or you can read it, but you can't write to it, write the value. It has to be an atomic write. Everything has to happen in sequence, and if it fails, all of it fails. That's a transaction. That's all it is. That's like if you go to the bank and you don't have enough money to take out of your bank, the transaction failed. No, I just didn't have enough money, or I had the wrong account number, or the bank was closed. The transaction failed.
Took hold was because it allowed programmers to write multi-user systems without worrying too much about the horrible complexity of concurrency. If you open a transaction, read some data, change it, and write it out again, the database will block any other access to that data while you're dealing with it. And as long as your transaction lasts, it locks access to the data. This was very good.
That particular data. You might be able to read other parts of it. It might actually lock the whole database, so you can only do one write at a time. Some let you do record-based locking. Ooh, so it only locks that record while it's being written to. So that's what he's talking about.
If this architecture fit your problem, it kept the programming model simple. It's still good if it fits your problem today, and it fits quite a lot of problems quite well.
Oh yeah, it's still good. That's mostly what we're doing with these things, is CRUD. CRUD makes a lot of money. CRUD is valuable. CRUD is useful. CRUD good.
However, as the web grew in influence and massive scale computing became more common, having a relational database management system as a synchronization point to your data, a source of truth, simply didn't scale.
Right. So if you've got a lot of things writing into the same database, you start to have bottlenecks. The bottleneck becomes the shared resource, because you're locking these things. So as you're supposed to, at least.
So people started experimenting with other approaches. I was once asked to consult on a huge project. They had decided to use a NoSQL database as their primary data store.
That just means it's a different way of storing data. It's not the standard transaction locking thing. It's just throw it in the data. You figure you better be careful with how you do this, because we're not doing anything. So it's very loosey-goosey. It's great for startups, right? It's great for like when you still don't know how your data is going to be structured and you're still experimenting. Great. And then you should eventually get to a SQL if you're going to have any kind of standardized data. Yeah, for sure.
Which is fine. but they'd forgotten or didn't realize the importance of the protection that transactions that they were more accustomed to had given them.
Now, some databases, some of these NoSQL databases have this transaction stuff, but in the early days, no.
This NoSQL database wasn't transactional. So data was shared by multiple processes and written to by multiple processes, and the results were essentially random. Whoever wrote last got to store their changes, everyone else would lose theirs, and without any indication of the loss.
Look, he's using the X.
It made me feel a bit queasy just to think about this big system with all the data shared and no protection or coordination between concurrent processes. This was a problem of not really thinking about the architecture of the system, but only the tools. That's not the same thing. A collection of tools alone doesn't make a software architecture. This team had seen one of the big web companies develop this great-looking NoSQL database to help them scale up, and it did that, but only in the context of a whole raft of other choices and constraints that this team hadn't thought to apply. There is another, somewhat similar, very common mistake.
Okay, so I just want to illustrate that point. It's easy to get this stuff wrong if you don't know what's going on. So let's look at how. So here's some code right here that we just looked at right here. How threads are compiled. Let's look at the thread example. And I've got this thing over here, so we can look at what it looks like with this race condition. So we got two programs here. We got this one here. Well, two functions. And then this one down here, right? So we're gonna run this part one first with the threads with the update problem, and it's compiling. So let me pause it. Okay, so let's do that again. So I do that. Oh, not this right here. So you can see at the end here, it's 188 out of 200. And every run, it'll be a little different. Let's try it again. So it'll be a little different every time because it's random. It's racing. That's another thing about these race conditions. It'll be random every time. That's when you know it's like, oh, I got a race condition thing happening here, because it'll be random. Like, why is this changing? I never get the same result. I can't tell where it's happening. That's the kind of stuff. So you can fix it, and the fix it runs exactly the same way, and you can barely tell it actually runs slower. It's slightly, tiny bit slower, right? But it's correct. So here's the second version right here. And what we're doing is this synchronizing. We're doing this synchronization lock. And Dijkstra, who was like the inventor of this whole thing, he came up with this little PV idea. Anyway, we'll get into that in a second. So fixing the race condition with atomic updates. Atomic meaning like an atom, you can't split it. It was back before they thought they could split out. So this idea is a mathematical one. And they come up with the idea of, they call it atomic. It's atomic updates. I was like, why do you call it? You mean critical structure, like a transaction? No, it's different. It's the same thing. Transaction, atomic update. I only get access to this thing. Nobody else can change it while I'm messing with it. Leave me alone. Let me mess with it. And so Dijkstra was the one that came up with some of this terminology. The basic synchronization object. She called this the bottleneck. So this right here. So he had this really crazy Hungarian acronym called P and V. P means wait for the lock. and then at the end of this scope here, where this synchronized block is over, that's when it releases. It produces. It consumes the semaphore. Like, all this word, really? You mean all it's doing is just waiting here, saying, hey, it's using this thing out here, saying, hey, I'm using this object right here, saying, as like a flag, saying, okay, I'm in the block now. I'm using the block. Nobody else come in. This guy comes in and he starts his function down here in thread 2. Starts his function and goes, hey, oh, it says, it checks here. Is somebody using it? Okay, I'll just wait. And it sits there and waits. Bing, 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 bing. I don't know how it does it, but there's a way that waits. It's either polling, or it's probably not polling, but it's probably some system table somewhere. It goes, hey, you got a guy waiting in line. Whoever's next, and whoever's that one's next, he gets the flag. The flag goes up again. This guy ends, right? He goes, okay, the flag goes down. This guy goes, I'm ready, I'm next. And the flag goes up for him. The flag is this thing, the semaphore. It just means flag. Just, hey, it's like a little, I got this. I'm using the thing now. And so I'm using this lock. I'm locking this thing, this resource, and this is just using it to use the flag. This is lock. This is, all it's doing is a flag here. It's all it's doing. So it synchronizes the lock. Okay, I got the thing now. It does its thing, and then I'm done. And then the next flag comes in, and it could be in order. This one could go twice. That one could go twice. This one can go 3 times. This one can go once. It's all random, but you're gonna make sure that the reading, the x plus plus here, x equals x plus plus. This x plus plus is a reading and a writing. So that's another thing too. When you see this, it's not just incrementing. It has to read it, calculate the new value, and then write it. So it's hiding. This is like notation hiding that stuff, because normally it looks like this: x equals x plus plus. I'll even put it over here. X plus 1. That's all that is. So it's x equals the read, x, and then the calculation, and then the write. That's what's going on there. So, all right. Let's see. Let's go on the next section here. So here's the diagram. So you have thread 1 and thread 2. Now we have this critical section. It's a critical section for the atomic update. for the transactions. This is a transaction section. So silly. All right, here's the shared variable. X starts at 0, so it reads it here. And it's locked. Now, people can read it, but you can't write it. So if there's any kind of writing going to happen, it's gonna have to wait till this is over. And even then, if you're going to be doing the reading and writing, you got to make sure you're inside a synchronized block too, because you could read it, right? But if somebody else is changing it and you're not in a synchronized block, the values might change. Sorry. And so that's why you have these atomic updates. It's just creating a different kind of bottleneck. So now, so it goes faster, yes, but you're still contending. We're contending for the same resource. We're going to fight. Fighting. I want it. No, I want it. No, I want it. No, I want it. And of course, you can get these situations where you have multiple resources and each one is needed by another one. And you can get these lock situations. That's why this kind of technique has been somewhat deprecated. Now that the computers are fast enough that we can, instead of having a shared resource that we're all updating at the same time, we just do copies. And that's kind of where the parallel processing is going. Is we're not doing these thread things anymore. We're just working on copies of things. So it makes it way faster. And then we got enough memory, and the machines have enough power to do that now. So, but at the time, this was a way to do that, to get up there. But boy, it really caused a lot of problems. So I do want to make you aware, of this chart here. Not all CPU operations are equal. So we're talking about these thread switches here. They're expensive. This is how much time. This is how fast light travels and the amount of time scale for this time scale. So it's like across your laptop screen. A photon will fly that fast in this time scale. And this is like a house, about 9 feet and 30 meters. So it goes all the way up. So you can see how fast things are by how long it takes light to travel, which is the limitation in the computer of how things operate. And in tiny, for tiny 1 or 3 operations, 1 or 2, small number of operations, the distance is always going to be small no matter what. But it starts to get really long when you start to add these operations up, which is these swaps. I took a screenshot here. Sorry, it's got a little cursor here. So here's the gates, the simple switching that happens down at the bottom. And then we got floating point addition and multiplication. Here's a return. Here's the cache off the CPU, reading the cache, writing the cache. There's function calls. There's another a Java style function call. Here's some more cache reading. Here's more reading from the RAM. And you can see as it comes up here, kernel call, when you're calling the system, all the stuff that has to happen. The thread context, when you're switching between these 2 threads, there's a cost involved. And the reason why I bring this up is because there is another way called coroutines to do with this problem. Now, this doing it with coroutines, with to fixing doing. Okay, so where is it? Yeah, here we are. Sorry about that. There we go. So with coroutines, they're much more lightweight, but they have to be built in to the compiler and the language to do this thing properly. So because what it's doing is instead of the operating system switching between doing the switching, it's the compiler writing code special. So in between every one of these lines in these launch blocks, in between each one of these lines is basically a sequence diagram where it's like checking to see which phase it's in of this particular function. It does one thing, then leaves. One thing, then leaves. And then the one thing, then leaves. One thing's, oh, my line this, my line this. So it puts like a little state machine that's invisible. You can't see it in here when you're inside these coroutine launch blocks. Anyway, that's kind of how it works. I know it sounds a little complicated, but it's just a different way of doing this, rapidly switching between tasks, trying to idea. It's just another way to do it. And it just so happens that the coroutines way is just so much faster. So it looks almost exactly the same. Let me clear this out. It looks almost exactly the code looks almost exactly the same. Actually, I'm going to change this to be more obvious because this is kind of hidden. It's kind of a C++ leftover. I mean, you should do it that way, but I just want to be pedantic here. Okay, so here's the coroutines with update problem, and let that compile. All right, there we go. So it runs exactly the same. It has the same problem right here. So coroutines don't fix it by itself. I was like, oh yeah, coroutines it fixes it. It's like, no, you still have the same problem. If you're trying to access the same resource here, it's gonna still have the same issue right here. So here's the fixed version down here. And all it's doing is it's using this mutable state flow as this is a type of structure that's designed for coroutines and designed for Kotlin. It just stores the value, and every time anybody that can subscribe to it, it'll automatically emit the value. So that's the whole benefit here for all asynchronous programming. And for doing UI work is mostly what I'm interested in. But I'm sure for backend work, this is also an extremely convenient way of doing things. So this is like the state of this is continuing. It's like a variable, except it's a little different. So it has this. It's a mutable state flow. It has this function called update that takes a lambda. It takes this little function right here, and it reads the value and then writes the value. So it reads the value x, right, and it gives it here. Just make it really pedantic. So x. So x. So update is a function that is a lambda. So it takes this current value of x, and it allows you to do the update on it. That's it. Oh, I forgot to change it to x here. X plus 1. There we go. I should have done the see if you do this like this, and you do Shift F6, which lets you change the variable. It'll automatically put it right there, which is kind of neat, nice feature. All right, so let's go run the second one. So this one's correct. So it's using this update thing here. And another thing about the coroutines is they run way faster. So let's go look at the thread the comparison between coroutines and threads, because they don't have that overhead of swapping here. So they don't have the same. Coroutines are doing the same kind of thread thing in a completely different way, but it's just way faster because it's just way more efficient. And this coroutine idea is way older than threads, way older, going back to the 50s, again 60s maybe. All right, so let's do the comparison. So here's an app, and it runs the number 100,000 parallel threads and 100,000 so 100,000 coroutines right here. Sorry, 100,000 coroutines and 100,000 threads, and it has some statistics here, and you should go look at this and play with it and change these numbers. It's sleeping 3 milliseconds, and so you have to use thread.sleep over here and use this delay for the coroutine. So it's slightly different syntax, but basically the same idea. So this 100,000 threads took 951 milliseconds. Now the threads is running. Same exact function. Same doing the same thing. Counter dot increment and get. This one take 8 seconds. So this one took about 1 second. Same thing. This one took about 9 seconds. So it's about 10 times faster. And you can do your own tests. So that's a good thing to know about coroutines. I guess up next is the conclusion. Oh, it's almost over. All right. I'm Chris. Give me a like and subscribe. And we're almost at the end of this. I'll keep adding more stuff to this thing and talk about these things. But yeah, I'll talk to you soon.